All right, what I want to do today, I want to do a little review. I think it really pays for us to take a little time and kind of review some of the concepts from Algebra 1. There's two things I want to do. I want to jog your memory. It's been a long time. But I also want to take stuff you already know and maybe ask you to think about that in a little, when we're here, earbuds and all that stuff, ask you to think about it in maybe a little different way. There's a reason for this. We're going to do, in Algebra 2, what we obviously do is extend on all the concepts from Algebra 1. So we're going to take the stuff you already did and we're going to push it into bigger and better and more difficult functions and things like that. So a lot of the same processes you did, we're just going to apply those to different stuff. Sometimes, though, I think what happens with algebra is, it's our math careers, they go for so long and they're so fragmented. You have different teachers every year, different people do things different ways. I think sometimes what happens to you guys as students is you develop the ability to get an answer without always really understanding what you're doing to get that answer, right? So let's back up and let's kind of talk about how we get that answer. So if you look at this packet, and I think we're only going to probably get through today, really I want to do just the first part. So we'll probably, it'd be nice if you could get through by the end of before tomorrow, see if you can work through problem 9 in that first problem set. We'll do most of them in class today. It's not really going to be much homework. I want to talk about what it means when they ask us to solve an equation like this, right? Okay, let's just start at the beginning. What does it mean to solve an equation? If I'm going to solve this, what's my answer going to look like? I don't care what it specifically is, but what's it going to look like? Okay, I'm solving for x, so I'm going to get an answer like x equals a number, right? Okay, good. How do I know if I'm right? If I plug it back in and it works, right? Okay, that's important, and I don't want to minimize that as a strategy. Whenever you get problems on tests, or homeworks for that matter, but I understand when you're doing homework on Moodle, a lot of times it's going to be, I would do the same thing. Because you can redo the problems, you're going to get an answer and plug it in and see if it works. That's fine. But on a test, one of my tests or an SBAC test or something like that, what should you always do when you have a question that says solve for x or solve the equation? Always should check. It's a free, it's like a get out of jail free card. You can plug it back in and you know for sure if you got it right. If you didn't get it right, then maybe you start over. If you did get it right, then enter your answer and move on, right? You can always check a solve type problem, all right? So when we solve an equation, so if we're trying to solve for x, that's the same thing. In math, we'd say we're going to find the value of x that satisfies the equation, which just means it makes it work, right? Okay, so how do we go about that? When we're going to solve an equation for x, what's the process we go through? Find null. Okay, so we've got to do some cleanup here, don't we? Right? How many x's are there in that original equation? How many different x's could you point to? 3, it looks like, right? I've got one there, I've got one there, and I've got one there. So solving for x, when I'm all done, I'm going to get something like x equals a number, right? We already established that. What could I call that process of trying to get an x by itself? I heard it. Say it. I'm going to isolate x, aren't I? So solving and isolating a variable are the same thing, right? How can I isolate a variable, though, if I've got 3 of them? I can't, right? Okay, I'm going to have to combine some stuff together. Once I get to a point in algebra, there's kind of steps to this, right? With a problem like this, we first have to get to a point where you can point to a single x, and I'll say this about 1 billion times this year. If I have an equation and I can point to a single x, then I can isolate it, right? And we'll talk about how we do that. But first things first, I've got to make this thing look simpler. So there's another word in math, simplify. What does it mean to simplify something in math? Put it in its easiest form. It is what it says, actually. We're just going to make it simpler, right? How do I know what steps to use when I'm simplifying something? How do you know what to do first? You probably, and here's another example where you just kind of know, but it's important to know. We need a little more than that. We need to know how do we know, because pretty soon we're going to deal with harder functions, and it may not be so obvious.
Parentheses or exponents.
Okay, so parentheses, exponents, what do we usually call that? PEMDAS, okay, order of operations. All right, so here's the first thing. Now, I'll make these notes available. If you want to write this down, this is a big thing. I mean, you're going to do this a lot. When you write PEMDAS, PEMDAS is spelled P-E-M-D-A-S, right? So what comes first? Parentheses. P stands for parentheses. It really stands for more than parentheses. What do parentheses do? They group stuff together, right? So anything that groups stuff together really counts as parentheses. So parentheses, P for parentheses, but really it means all grouping symbols. After P comes E, right? What's the E for? Exponents. Okay, here's where we got to be careful. PEMDAS is spelled P-E-M-D-A-S. So does that mean the M comes before the D?
No.
No, it doesn't. You're right. The M and the D are on equal footing. So here's how I want you to write this. We want to write the M and the D on the same row to remind ourselves that they're equal, right? When we're simplifying, when we get down to this row, we're just going to do all multiplication and division, whatever comes first, from left to right, okay? And then finally, what about the addition and the subtraction? Are they equal? So I'm going to write the A and the S together like that, right? And so this is the normal direction. That's the direction we go when we're simplifying something, right? Is that all making sense? So now that, you already probably know the steps to do, but let's just show here that they fit into this scheme. So the very first thing we'd look for is inside parentheses, is there anything we can make simpler? Well, there's only one set of parentheses. Can I simplify 2x minus 5? I can't, right? So that one we can skip through. We just check it off. You see any exponents? No. So we can skip that one. But there is multiplication and division going on there, or at least multiplication, right? Where is their multiplication? Okay, right here. This. This is kind of important. Let's just take a second and talk about that. And I know we're kind of going back to basics here, but it's really good to make sure everybody understands this well. Let's take that part. In fact, I'm going to go to a different page. We'll come back to this. Was it 2x plus 5 or minus 5? Minus 5. Okay, that is a product, isn't it? Product is what we have when we multiply things together. How many factors are there? What's a factor? See, these words we throw around. We've got to make sure we all know what we're talking about when we say these words. Factor is an important math word. Factor, we can make it real simple. In math, factors are just things being multiplied. So how many things are being multiplied there? Two. There are two things. There's one thing, there's one factor, and then this whole thing counts as another factor. It's in parentheses, right? In math, when something in parentheses, we call it a quantity. And why do we put things in parentheses? We group them together so we can multiply them or take them to a power, right? So this is the first factor, that's the second factor, two things being multiplied together, right? We recognize that because the 3 is next to the parentheses, and when things are placed next to each other in math, it means they're being multiplied, right? That's implied multiplication. Like we would say 3x means 3 times x, right? Okay, one more step here. If we look at this second factor, I just want to throw another vocabulary word out here for you. And we'll go through these again and again. You know, you'll get this stuff real soon. What do I call the 2x and the 5 if I'm just focusing on this second factor? Anybody know? What do I call things that are added or subtracted in math? Thought I heard it, yeah. Well, sometimes, I mean, this is an integer. Integer is just a set of numbers. We'll talk about those pretty soon. That's not what I'm looking for, though. No, a sum is when you add things, but a sum of what? What is it? What are the individual things you're adding called? I mean, they might be variables or they might not be, but that, once again, that's specific. Have you heard this before? Terms. Remember talking about that? Maybe? Terms are just things that are added or subtracted. So inside these parentheses, I've got two terms. I've got a 2x and a -5 that are being combined with addition or subtraction, whatever you want to look at. Right? Does that make sense? Okay. All right, so going back to our problem then. First thing we got to do here is we got to do some multiplication, don't we? That's when we finally get down to actually able to do something. So we multiply the 3 times the quantity 2x minus 5, and what does that give us?
6x minus 15.
Everybody agree if I distribute the 3, that's what I get? Okay. And then that's the only multiplication, isn't it? So then up here I've got a minus 3. On this side I've got a 2x plus 8 plus 6x. Okay, good. So we made it through that step. Now we've got add and subtract. Now what? What can I add on the left side? Any like terms I can deal with?
Negative 15 minus negative 3. That left equals negative 18.
Okay, so that makes sense. Now that's another place where I think people sometimes, there's a little bit of confusion. If I take negative 15 and I subtract 3, whenever I subtract a number, that's the same thing as adding what?
Negative.
Adding a negative, right? So subtracting 3 is the same as adding negative 3. So negative 15 and then another negative 3 plus negative 3 would be negative 18, right? So on the left side, we get our 6x minus 18. How about on the right side? Any like terms?
2x plus 6x.
Okay, 2x and 6x makes 8x, and then I've also got an 8. Okay, now we're getting down there, right? Things are looking better. We're simplifying stuff. There's even more we could do. I'm not to a point yet where I can isolate an x. I still have 2 x's. How can I fix that?
I've got 6x from one side, then do it to the other side.
Okay, we can combine those x terms, can't we? Now let's just talk a little bit about that. There's 2 options here. I could either subtract 6x from both sides or subtract 8x. Which is probably preferable? 6x. How come? Okay, good, because I'm going to end up with a positive number of x's, which sets us up for easier algebra later, right? Okay, I like to talk about algebra, and I want you to kind of think about this almost visually a little bit. What I would say here when we talk about this, I would say we're going to push the 6x to the other side, push it to the right. The way we do that algebraically is we subtract 6x. But really what we've done is we've pushed that term over there, right? And then at that point, we end up with negative 18 equals how many x's? 2x plus 8. Okay, now things change. All of a sudden, how many x's are there up there now? 1. If I can point to a single x, I can isolate it, right? Okay, so here it is. There's my single x. Okay, now what? Now we're going to go back to our order of operations, but instead of going down from top to bottom, which is what we do when we simplify, we reverse them. This is, you may not be familiar with this, but this is probably the most useful part of order of operations, is when we go bottom to top, and we do that to solve or isolate, same thing, right? So now we've got a single x we can point to, we're going to isolate it, so let's work bottom up. First step would be adding or subtracting. Do I need to add or subtract to get that x by itself?
No.
What do I do? Subtract 8, okay? And look what we're doing. We're gradually paring everything away to get the x by itself. Let's just like strategically think about the steps. First I subtract 8, then I divide by 2, and then the x is by itself, right? Okay, and this is what tells me the order. First I add and subtract, then I multiply, or in this case divide, right? And so we end up with
You get 26,
You
and then
didn't
you divide that by 2, and you get
oh yeah, okay, I got you. You finished them. I see where you're going. And now we divide by 2, and we get x equals negative 13. This is a test, what should I definitely do? Plug it in and check it, absolutely. Okay. Because we're short on time, that's the right answer, I'll just tell you. Okay. All right, good. Does that make sense? Right, so once again, the thing I really want you to get out of this is, you simplify by going down, and if we're solving a problem, yeah, we've got to simplify until we get a single variable by itself, and then we turn around and we isolate the variable. Okay? Once again, you know this stuff. You could do these problems right now, but later on in my AP Calculus class, we still do this stuff. It's the same stuff, only maybe it's a little more advanced, the functions we work with. So instead of just, you know, linear equations like this, maybe we throw in some sines and cosines. But it's the same idea. All that stuff still fits into the order of operations. You're solving even more difficult equations like that. Okay? All right. So next, try something like that. I want you to just at least get a start on this. I want to see what you do with this. How many x's are there up there real quick? 3. Okay, so what am I going to definitely have to do first? I'm going to have to simplify, right, until I get a single x, and then I will, once I get a single x, what do I do with it? Isolate it. There you go. Right. Let's talk about this a little bit. This is a little tricky. There's something on here that's a little different. When we're trying to simplify, you know, once again, we can skip through the parentheses. There's nothing in parentheses for us to do in this case. No exponents. What about the multiplication? Somebody give me one example of the multiplication issue I deal with.
5.
There's a product. 5 is being multiplied by this quantity, isn't it? Right, so we're going to have to do that. That's one of them. There's another one.
Negative to the x.
Ah, right here. Okay, yeah, let's talk about this now. What's being multiplied here? I've got stuff in parentheses. Okay, good. When I subtract a set of parentheses, technically what's going on? We don't write it, but what's the number that sits out in front of the parentheses here? -1, right? Does that make sense? Okay, parentheses. Think about parentheses. Why do we ever use parentheses? What are they for? What good are, let me give you an example. How about something like this? What if I've got the quantity x plus 2 plus 5? Are those parentheses doing anything? It does. Are those useful parentheses?
No, it's just.
Totally unnecessary, right? Totally unnecessary. They don't do anything. The answer is just x plus 2 plus 5, right, which is x plus 7. Agreed? Okay. They're unnecessary. What's the number out in front of those parentheses? 1. Multiplying by 1, does that change anything? No. 1's the multiplicative identity, right? It's our identity number for multiplication. Multiplying by 1 keeps something the same. So I don't even need them there, right? How about in this case? There they mean something, don't they? Right? Because I'm multiplying 2 times that whole quantity. So because the number out in front is a 2, yeah, they're there for multiplication purposes, right? What if I did something like that even? Well, now it's even, now that whole quantity is being cubed also, right? We'll get to that stuff later. You get the idea? So parentheses are only useful for when something's being done, multiplied by it, for example, or is taken to a power, right? So in this case, there is a number out front other than 1, and so we have to distribute it, don't we? Right? The parentheses are there for a reason. Okay, what's that going to give us then? If I distribute the negative 1, what am I going to get?
Negative plus 43.
Okay, I got my 6, and then I get a negative x, and negative 1 times negative 3 is plus 3. Now, how can we maybe even simplify this for future reference? If I'm distributing something like this, I don't even have to write the 1. It's essentially the same thing as distributing the negative sign, isn't it? Right? Isn't that all you do when you multiply by negative 1 is change the sign? Right? Okay, good. So now, on this side, this is a little easier, more straightforward. Multiplying the 5 through, I'm just going to get, what, 10x minus 5. And now it's no big deal, right? From there on out, I'd say probably things are a little easier. Now we're just going to combine like terms. On the left side, what, 6 and 3 is 9. I've got a negative x. 3x and 10x is 13x. Where am I going to push the x's? Good, push them to the right. 13 is bigger than negative 1. So if I add x to both sides, how many x's are going to be on the right? And then I'm left with just a 9 on the left and a minus 5. Now, what are the 2 steps? That's a 4. What are the 2 steps in order to get the x by itself at this point? Add 5. Divide by 14, right? And if I do that, if I add 5, I get a 14 over here. Now if I divide both sides by 14, 14 divided by 14 is 1, right? Okay, make sense? All right, good. Okay, next issue. How about something like that? Okay, let's just talk about this one for a second before you jump into it. This looks bad, obviously. How come? Fractions. I don't know, we got to deal with fractions. Fractions are just numbers. You know, the same properties apply to fractions and apply to integers, like in that last problem. We can still add and subtract and multiply and divide fractions just like any other number. It's just more cumbersome and difficult, right? More chance for a mistake. So that's the problem here. It looks like, yikes, now we're going to have to do something like maybe push the x's over this way, subtract 1/6 x from both sides, and I'm going to have to deal with the, adding and subtracting fractions. Any other suggestions?
You can make them all decimals. You can make it all numbers, but this 6, the x set 6 into decimals, because then the x is set to divide by 6.
Okay, I could, and by the way, x divided by 6, isn't that the same thing as 1/6 x? Everybody agree? Okay. I could do that, and I'm glad that's brought that up. What's the problem with using decimals here? Are there any problems?
You won't be close to your answer because if you, everyone could use a different part of the decimal and get a different answer.
It's going to work fine for some of these. 3/5 x is exactly equal to 0.6x, isn't it? 3/2 is exactly 1.5, right? What about 1/3 though? Oh, I can't represent that as a decimal Really? I can't I? I can't write it as a complete decimal because it goes forever. And so any decimal I use is going to be imperfect, right? Does that make sense? So decimals really don't help us a lot here. It's a good idea. Other suggestion?
Find the common.
Ah, perfect. Okay, there's a great trick. Here's the trick I'm looking for. So there's a trick called clearing the fractions. That's what this is. And there's a good reason for this. It'll make sense. Now think about, wouldn't it be nice if I could get rid of the fractions by multiplying by something, right? What number could I multiply everything by? Well, if I multiply 3/5 by 5, that would be good because the 5s would cancel. But that doesn't work for the 1/3, right? Well, if I want to find a number that would work for both 5 and 3, what number would work for both? 10, because 3 doesn't go into, I heard it, 15, right? How come? 15 is the least common multiple of 5 and 3, meaning it's the smallest number they both divide into. In adding fractions, we'd call it a common denominator, right? If we add fractions up, don't you always have to get a common denominator? Well, 15 works for the left, but this is an equation, isn't it? Because it's an equation, you know, the properties of equality that we'll talk about essentially are summed up by one statement. When you have an equation, you have to treat both sides equally, right? Okay, so we have to do the same thing to both sides. So if I multiply the left side by 15, I'd have to multiply the right side by 15. That doesn't work so well, though, right? So I've got to look at all the denominators on both sides of the equation and come up with the least common multiple, or the least common denominator. So what's that going to be?
30.
It's 30, isn't it? 30 is the smallest number they all divide into. What happens if you don't get the least common denominator? What if I picked like 60? It's still going to work. Just it's going to be a little bit harder to do because you're going to get a little bit numbers that are a little bigger and harder to deal with, right? So you want to try to get the smallest one. So we're going to multiply both sides by 30 because 30 is the least common multiple. If I write it as LCM, do you know that means least common multiple? Have you done that in the past? Okay. The least common multiple of all the denominators, right? So here's how we do this then. We're going to put brackets around the left side and multiply by 30, and I have to do the same thing to the right side because it's an equation, so I'm going to distribute a 30 through. But here's another part of this where I can help you out, where we can make this a little bit easier. When I multiply fractions, I multiply straight across, right? So this is the same thing as 30 over 1. Everybody agree? If I want to think of it as a fraction. So if I want to multiply 30 over 1 times 3/5, normally we would multiply straight across and get 90 over 5. Well, real quick, what's 90 over 5? It's hard to do, isn't it? A little bit. No. 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 My point is, that's not a really super simple thing to do, right? To simplify that big fraction, 90 over 5. It's 18 is the answer, right? But you got to really kind of think about that a little bit. And it could be worse. What if it's an even bigger fraction? But you don't have to do it that way. Think about this now. 30 is a special number. We built 30 specifically from all these denominators. We handpicked the number 30 because that's a number that they all divide into, right? Everybody agree? So why not instead, when we're distributing this through, why not reduce first and then multiply whatever we get by the top, right? So here's how I like to show this. I think, why don't you try it this way? I think you'll like it this way better. 30 over 5 reduces to what? 6. So then I write a 6 up there and it points at the top. 6 times 3 is 18. That's easier, isn't it, than dividing 90 by 5, right? So my first term is just 18 and then times x. 30 over 3 is 10 times 1 is 10. You get it? 30 over 2 is times 3. Okay, and then finally 30 over 6. times x. Okay, now, that's easy. I'm not even going to go any further, you guys can do that. Right, once we get to that point now, we've cleared all the fractions out, we'll just combine the x's and then isolate x, right? Make sense? Okay, good. Do number 7. Excuse me. right, let's talk about this one. Looks like we're, you know, it's, the fractions throw people off. Fractions make people tense. When you're tense, you don't do good math. So let's think about this one a little bit. All right, so using a D instead of an X, that's fine, doesn't matter. Same idea. Okay, what's the least common multiple of all the denominators? 8. Good. And if you picked 16, it's still going to work, right? It's just, it's a little easier to do with an 8. So we'll distribute an 8 through. I've got to put everything in parentheses on both sides. And let's do my trick, right? 8 over 4 is 2 times 3? 6. So the first term is going to be 6, and then I times D, right? 8 times 1/2, we can probably just do that in our head. What's half of 8? 4. So I'm going to get a minus 4. If we do the trick, we just get 4 times 1, right? How about over here? 8 over 8 is 1 times 3 just gives us 3. 8 over 2 is 4 times 1 times D. 4D, everybody agree? Okay, from there it's no big deal, right? Which way would we push the D's? Good, to the left. So if I subtract 4D from both sides, I'm going to get 2D minus 4 equals 3. What are the two steps in order to get the D by itself?
Add 4, divide by 2.
Good. Add 4, divide by 2. And we can do that in our head. Right? If we add 4, what am I going to get on this side? And then I'm going to divide by 2, and so D equals 7/2, right? Okay, good. All right. Last issue we want to deal with, not that one. And we'll call it a day after this. When are we out of here?
1 minute.
Oh, okay. Maybe we won't. We'll call it a day right there. How about?